Morning. My name is Bob Spindel, and I'll be the moderator for today's session. It's really wonderful being here to take part in the celebration of Walter's 100th birthday. For many of us, Walter has been a teacher or a mentor, a role model, a colleague, a friend, and also an inspiration. And for many of us, he's been all of those things. So this is just wonderful. It's going to be a great day. We have a lot of people to thank for making it happen, especially Bruce Cornell and Peter Worcester. Thank you very much. I look forward to it. And let me just say a word to the speakers. If you see me, well, there's all kinds of timers up here, and there's a big clock, so you can judge your time. But if you see me waving my hands, you know your time is up. And if you see me stand up, I'm coming for you. Okay, so it's my pleasure to introduce Margaret Leinen, the director of the Scripps Institution of Oceanography.
Thank you, Bob. And thank you so much for being here today with us as we celebrate this year of Walter's 100th birthday. We know that many of you have traveled a long way to be with us. We really appreciate it. You honor us with your attendance. And of course, we all honor Walter in this amazing year of celebration. We started the year in February with a symposium at Oceanology International on ocean observing technology and systems. We continued in May with a symposium on waves and tides. And some of you, Carl especially, were here with us for that. We now have this symposium, and in October, on the 18th, we'll have a birthday party for Walter here at Scripps and in the community. And October 26th, a very special dialogue between Walter and Prince Albert II of Monaco. And many of you know that Prince Albert's great-grandfather, Prince Albert I, really started oceanography in Europe, purchased oceanographic vessels, participated in exploration himself. And so the Prince and Walter will have a dialogue about this amazing history, this amazing time that we've been through as oceanography started as a discipline, and where we have come, or how far we've come, and where we're going. It's really a pleasure and an honor to be able to look back with Walter on a century of wonderful exploration, a century of wonderful insight and participation, and 75 years here at as an active oceanographer. I think it's very appropriate that this symposium is focused on ocean acoustics and national security. As you know, Walter's work with Harold Sverdrup to predict waves was very, very important during World War II and enabled many of the landings that gave the United States a tactical advantage during World War II conflicts. His expertise in ocean physics and ocean acoustics also has given the U.S. military the edge in submarine warfare during the Cold War. He has conducted a lifetime of research with the Navy and still holds the Secretary of the Navy, Chief of Naval Operations Oceanography Chair here at Scripps Oceanography. And as he may tell you later on, he also has an active ONR grant and is trying to finish a paper from that grant before October 19th, the big birthday. So nothing like having a deadline to motivate you. It's been really inspiring for us at Scripps to have so many people from the community come to share the science that has been inspired by Walter, to share your stories of the amazing impact that he's had on you and on our whole field. And I think that one of the things that's very special is we have several of Walter's students and several of you who, as students, were inspired by his work. And that's very much a part of the legacy. All of us at Scripps know never to schedule anything associated with Walter without including graduate students. And it's not allowed. And it's really that strong sense of not only looking back on the history of oceanography and the history of our field, but investing in its future that is so very much a part of Walter's legacy and something we honor today. So he always pushes us. I assure you he pushes me, and always about the science and how to do new things, how to be more thoughtful, more daring in what we do. And of course, with a very strong emphasis on actually getting out to the ocean and making measurements, making sure that we have the full complement of tools and that ability to find new things that we hadn't seen before. So before I turn the microphone over to Frank Herr from the Office of Naval Research, I'd like to give a quick thanks to some of the people who made this symposium possible. That certainly includes our friends and colleagues at ONR and NOAA, who supported us financially. Certainly Peter Worcester and Bruce Cornell, who worked hard on the organization of the event, and special thanks to the Munk family for your support in making this happen. So now please join me in welcoming the head of the Office of Naval Research, Ocean Battlespace Sensing, Frank Herr. Frank.
Well, you'll hear these words again and again today. It's a pleasure and an honor to be here to help kick off the symposium. I've known Walter now for almost my entire career, so the entire time I've been at ONR, and it's been a real pleasure. I was talking to him earlier on. It was about the time that he was reaching 65, and I was a young program officer at ONR coming out on my second site visit, didn't know anything, and it was very nice to be wrapped around the shoulders with the kind of friendliness that we've all talked about and you all know about. So I bring greetings from the CNR, Rear Admiral Dave Hahn. He very interested in oceanography, sees the future as being a decade now that we need a lot more oceanography, and he's talking to CNO a lot about these sorts of things, and so we'll see how all this develops. We have something called Task Force Ocean. I wanted to say a few words about Walter's legacy and a couple stories that I know. So bear with me. I'm looking at the clock here. I don't think I'll go over my 15 minutes. So Walter's swath through basic research in physical oceanography, acoustics, and geophysics is broad and deep. And the influence that he's had on the Navy over this time is also very broad and deep. And there are a number of different elements that are occurring today that people use regularly that are embedded in the way that the Navy does business that can be directly related to Walter. Margaret mentioned the issue of the forecasting of waves during World War II and Operation Torch and then D-Day. It turns out that we have an operational system today that does something very similar. It's much more computerized, you might imagine. It's a bit more standoffish than people were trying to get data from during World War II, but it works very well, and it's really nice to know the connection that occurs from something that's still useful today and the science that was developed early on in that regard. Clearly, the work that Walter's done, the choices he made to develop new kinds of research and to ask certain kinds of questions during his career have opened up so much new research for so many of all of you and many others. It's a wonder. There's a lot of terrible things that happen as you get older. Of course, you get old, but one of the beauties for a person like Walter is to be able to see that opening up of the research front based on the sorts of things that the questions you were asking, simple questions maybe, back earlier on that have become more and more important later. The development of what we would call an avalanche of research coming from that single stone or small snowball. And the other thing is that not only is Walter been impactful based on his research and all the students that he's developed and all the people that he's influenced, but behind the scenes, he's helped us in many different ways, providing appropriate advice at just the right time to do certain kinds of things. I have three examples that are, I think, very illustrative. One was told to me by Fred Sawfeld years ago. Fred was the executive director of ONR, and I think this was probably in the mid-90s or so, that Walter had a visit to Navocino and was quite interested in a new type of research that we had been pursuing that was now a new tool at Navocino called data assimilation. And at that time, data assimilation was a tenuous transition of S&T into more operations for the models. And Walter turned around and ballyhooed the idea of data assimilation to senior leadership, and I believe actually called a congressman or two and talked about the value that was being presented in data assimilation. I think as it was presented to me by Fred, it was a very seminal time. It was exactly the right thing at the right time to be able to put such a new tool into a firm foundation in the command. Second example is one that I know personally, because Walter used to talk to me a lot about the need for ONR to get back into the Arctic. And we went back and forth for a couple of years where Walter would say, "Frank, you need to be in the Arctic. Here's the reasons why." And I go, yes, sir. We're thinking about the Arctic. I'm looking for funds, et cetera. And he goes, "You need to get back in the Arctic." And then he started to talk to my boss, CNR Nevin Carr at the time, and then I got to talk to Nevin Carr more easily about the issue of being back in the Arctic, and now we're back in the Arctic with both feet, and it's been great, and the research is going very well, and I have Walter to thank for that push, right at the right time, to do the right thing. The third story Walter told me, and this one goes much farther back. Back at the beginning of the Cold War, Arleigh Burke, who was then the CNO, was very interested in developing the oceanographic community, and so he set out to help institutions like Scripps. There's a whole group of them, and one of the things that he wanted to do was to get out to sea more. And so, as Walter told me, there was quite a discussion at that time of whether to bring academic oceanographers into close proximity with naval oceanographers by sending, and naval officers, by sending these academic oceanographers to sea on naval ships. And World War II, things were done that way. Soon after the war, things were done that way. But now we were developing a new approach for oceanography and engagement of the academic world. Which way should we go? Should we put oceanographers on naval ships, or should we build purpose-built platforms that, or in the civilian world, the oceanographers could have their own platforms, operate them as they needed for their science, and of course we know which way it went. And so that element of having discussed, having had an opportunity to be impactful with the right decisions, the right time, and now you see the results. We're on our third generation of oceanographic ship. The Sally Ride is in that third generation of purpose-built oceanographic ships. And Melville was in the first generation, and then we stretched it. It's a lot of what we see goes back to the right decisions at the right time. So before I sit down, though, I want to say a couple words about Walter and his interest in people. I've seen the student issue. I know exactly what Margaret was saying. Walter's always been so strongly interested in people and mentoring, and young scientists as well as graduate students. And recently I had an instance to hear about this firsthand from a military deputy, a naval captain that came to work with me back in the late spring, stayed on through the middle of the summer. Captain Rob Sparrock. Rob is the military deputy now for the second person in the second highest person in the Defense Department, and Rob was a student for Walters, and he would tell me, as I said, "Rob, what'd you do when you were at Scripps?" He goes, "Oh, I worked for Walter Munk." I go, "Wow, how about that?" And so then he would tell me stories, and they're all great stories. And so Walter, thanks for all your help with all the students and your interest and your ability to convey to those students the joy de vivre, and so that research isn't all drudgery. There's an adventure that goes on when you're doing research and you're connected with an appropriate person. So finally, I also want to say that the generosity that the monks have had over the years to entertain ONR in a setting where we can bring together the institution and the ONR groups of people who have come out here has been terrific. Many times business develops at Walter's house, which then has high impact. And Mary, you've done just a great job in recent years here keeping Walter straight. You are a terrific a partner for him. And thank you very much for your hospitality as well. And it's just terrific. So we got a really good-looking couple here. I'm very pleased with that. You know, Walter, you are so lucky in love, I tell you. And okay, so that's my time. Before I sit down, though, I would like to tell you that the Oceanography Society, and with ONR's help and sponsorship, have decided on the next Walter Munk Award recipient, Dr. Andoni Lavery from Woods Hole. And I'm sorry that Andoni couldn't be here. We were hoping that she would be able to be here and help us to celebrate. So a hand for Andoni. And with that, I'll turn it back to Bob. Thank you, Bob.
Thank you. Someday we need to have a symposium where all we do is tell stories about Walter, right? Anyway, thanks, Frank. The next speaker is Carl Wunsch from MIT and Harvard, and he's going to talk about the beginnings of acoustic tomography. I don't know how to start the timer thing.
There's no mobile mic.
This one runs automatically.
Not that I know.
Sir?
It works pretty well.
Okay. Okay, well, thank you. Of course, as always, I'm pleased to be back here. For many years, it was kind of a second home. But Bob did refer to Walter's mentoring and supporting role. I should tell you, though, that I decided years ago that Walter was a hopeless role model. I could never be like him, mentally or physically. So I think that as an inspiration, he's unmatched, but as a role model, I would say watch out. The theme here is primarily acoustics, and of course Walter told the speakers to look to the next 100 years, which I'll come back to at the very end, but to look forward, you've got to look back. And I thought it would be interesting to try to explain how we came to produce this thing that became known as acoustic tomography some years ago. And this is a non-technical talk. I think there's one equation, one very simple equation in it. And I need the indulgence of the acoustic people in the audience because it's mainly not about acoustics. It's going to be the story of how we brought together two very distinct fields. I will say at this point, because I'll probably forget later, is that Walter is one of the last generalists, I think, oceanographer who could work on 15 different fields, and I think tomography is an example whereby bringing together elements of extremely different fields that led to something that is very useful, although you have to decide that. It was an accident, as it says there. There was a Jason Summer study that I came out here for, and we were meant to be talking about, well, what it says, a supposed breakthrough that the Russians had made in detecting U.S. submarines. And this was very worrying because this was part of the mutually assured destruction equilibrium, and should the U.S. Submarines be suddenly vulnerable, it would have been in some ways catastrophic. So I came out, and this was the reason we were paid. I suspect ONR had put up a fair bit of money for that, among other things. And we started talking, as I hadn't seen Walter for any period since he'd had a sabbatical at MIT, I think in 1969. And so we had some years of catching up to do, and we would just start talking about what he was doing, what I was doing, and he had a student, Peter, and they'd been doing reciprocal transmissions. And I had been doing something completely different, and I will try to tell you how we got it together. There's the three of us some years later. That's actually Venice. I couldn't find a picture of the three of us from 30 years before, but at least there is one. For me, acoustics was a kind of a closed book. I think those of you in the audience trained as sort of conventional physical oceanographers, we never learned about acoustics. It was something you used for depth sounding, and there was these novel ideas about tracking floats that Tom Rossby was a pioneer of, and they were used as acoustic releases, but it was certainly not part of the academic scientists. And a lot of the work in acoustics, just as a practical thing, was classified. And so this was not something that was on my agenda. And I came out here not thinking we were going to talk about acoustics, but it's the way it worked out. I was working on what some people will call inverse methods. They have a very long history, although that label is of comparatively recent origin. If you look at some of Gauss's work on determining planetary orbits from a few noisy positions, he was really solving an inverse problem, and even he had predecessors that went way back. And there is this issue that there are inverse models, so-called, and then there are what I would say are inverse methods, which are much more general and you don't have to worry about here. And I didn't know much about this either, but I got involved with the work of this man many of you will have heard of, Valentine Worthington, Val Worthington, who had been working for his whole career basically on the general circulation of the North Atlantic, and he wrote a book. It came out, I guess it says 76, maybe correct, in which he attempted to once and for all define the circulation of the North Atlantic Ocean. And what he had done was he had taken the very classical hydrographic stations in those days, still mainly Nansen bottles and reversing thermometers, and he tried to piece them together into a circulation for the North Atlantic. And he had struggled with this for years because he wanted to conserve things like temperature, heat, salt, so forth. And he found he couldn't do it. And as I'll show you the pictures in a minute, he finally decided that what was wrong was that the ocean was not in geostrophic balance. And if you don't know what geostrophic balance is, it's fine. But it's basically Newton's laws in a rotating frame. And he tells you, so he was going to give a talk, and I typically went to talks about almost anything, but I went along to hear what Val had to say. He was going to summarize what was in this book. And the problem is with it was he tells you in a footnote, it's in a small footnote, you have to read the book very carefully, where he simply tells you that he has violated a geostrophic balance, and in effect, he was violating Newton's laws of motion. F was not equal to MA. This seemed rather bothersome. The audience, as I remember it, was pretty passive. They said, well, Val says this is the way it is, this is the way it is. But there was a basic problem of physics. How could you get a flow that didn't satisfy F equal MA? So, and this is a famous picture. For many years, it was widely publicized and put in textbooks as the North Atlantic circulation. That's what it's supposed to be. You see the Gulf Stream. There are numbers attached to the transports. You see that very intense westward flow south of the Gulf Stream, and then what people started to call the Worthington Gyre up to the northeast. And the trouble is, it violates Newton's laws, and didn't bother a lot of people, but I thought, well, this can't be true. And so what to do? And so I had been a graduate student in geophysics, and I knew about Backus-Gilbert, which of course was, I guess, up the hill that way, about inverse methods. And it was a very highly developed subject by then, and so I knew it superficially. I started to read George Backus's papers. George Backus, is he here in the room? This was, one of the kind of summarizing papers, and I was having a very hard time with it, although I knew some mathematics. And it's not easy going because he cast it in the language of functional analysis, and he was proving theorems, basically, about it. And so there is this question of what is an inverse problem. The most famous one is quite different from the one that I was going to be faced with and that we used tomographically. The most famous one is this one that's called Can You Hear the Shape of a Drum? Which some of you will know. As posed, it says, if you know all the frequencies of free vibration, could you figure out what the shape of the drum had to have been? It took about 50 years to answer that, because Kotz's paper, which I then read, basically said he didn't know the answer. About 50 years later, it was proven that the answer was no. But that's a mathematical, Kotz is an important mathematician. That's not the practical inverse problem that we were faced with. And a colleague told me to read Ralph Wiggins' paper. Some of you may have known Ralph. He was a student when I was. And Ralph did something that at the time seemed very radical. He rewrote Backus-Gilbert in discrete form. Turns out if you are dealing with stochastic systems in particular, if you make it discrete, most of the interesting mathematics goes away, and it's much simpler. And that got me started. And here's the only equation, it's circled in red, that you have to pay attention to. I asked Worthington what it would take to convince him that you could solve the problem geostrophically, so that F equal ma was restored. And he said, I'll show you a picture in just a second, that if you could balance mass and heat and salt and so forth in a bounded region of the ocean, you could convince me. And the whole point of this slide is that all you had to do was write down equations that said the flow into a volume of ocean had to be almost equal to the flow out. It shouldn't be exactly equal because everything was noisy, but approximately so. And so once I realized this, I could write down what are just a set of linear algebraic equations. The problem from the mathematician's point of view, it was twofold. One was there were fewer equations than unknowns, and they were noisy. These were not perfect, so people like Mark Kotz would not have been interested in that. But that was the gist of it, and the minute one got it in that form, the problem went from there being no solution, which was Worthington's conclusion, to there being an infinite number. And but he had based a case of whiskey that it couldn't be done, and these are just examples of doing it. And I won't trouble the audience with what these things show, except that just in these lower two here, you can see two top to bottom circulations that were both completely consistent with the data. And the part that troubled a lot of people is in the lower right. There was no level of no motion. Everybody was looking for a level of no motion. And these were columnar flows. The dashed regions are flows toward you. The clear ones are flows away from you. And you can't look at that and say, oh, there's a depth like 2,000 meters where the flow goes to zero. It simply wasn't true. This was very unpopular because all the textbooks, Sverdrup, Johnson, and Fleming, which also came out of here, did talk about determining the level of no motion. And I talked about this in Woods Hole, and at the end of my talk, Worthington stood up and said, well, he had bet a case of whiskey that this couldn't be done, but he didn't understand anything I had said, except that his friends had told him that the problem was solved. So he decided that it was worth a case of miniatures, which, of course, I couldn't argue with. Hadn't done it for the whiskey. I kept a couple of those around as a souvenir for many years until my children got old enough to drink, and then they vanished. So I no longer have these things. This was an interesting Scripps connection. The sort of the mathematical guts of linear inverse problems these days, you'd say, is the singular value decomposition, although it wasn't called that. In some ways, the ironic thing was it's usually attributed by historians to Carl Eckert, who, of course, was the director here and worked here for many years. And he didn't occupy the IGPP office right next door, sequentially, I guess, to Bacchus Gilbert. And I always wondered whether they had ever gotten together and to talk about the fact that something that Eckert had done in 1939, he actually had an earlier paper as well, was the guts of the practical application of Bacchus Gilbert. I suspected not. Eckert had a kind of a history of not being credited for things that he had done, which were then ignored or set aside. But I'm not sure there's anybody else in this room who remembered that. This is just basically to say that the singular value decomposition, which if you don't know what that is, it's okay too. It's not essential to this, has been invented over and over and over again. And the problem is what it says down there. It's become a Tower of Babel, that people reinventing the same, then the list is incomplete, I could add to that, not bothering to say, isn't this known? Aren't there methods, computer codes, things that I could use if I'm willing to look at goes on in allied fields? This is the generalist question again. Okay. There were antecedents. This is a kind of an interesting one. This was a reprint that Henry Stommel gave me. He signed it, and he wrote up in the upper left-hand corner, I guess I can read it. This is a most mysterious method, HS. And Hidaka, 1940, not a very propitious time for communication, tried writing down equations to balance the flow into that quadrilateral and into the subtriangles there. And he wrote down the set of equations. And he solved them, of course, by hand, which pre-computers was a major undertaking. But then Desfontes, who also has connections here, after the war, showed that the equations were what are called ill-conditioned. You made the slightest change in one of the coefficients, you'd get a completely different solution, and that killed it. And nobody tried to do it. I guess until I came along, not realizing that Hidaka had done that until later when it was pointed out to me. And then there are a lot of things that one could say. George Needler, years later, proved that there was no level of no motion. If you had the density field, you could actually calculate the three-dimensional flow field. It's not practical for an observer because it involves third derivatives of the density field, but as a mathematical statement, look in any oceanographic textbook before about 1980. It will tell you that the serious problem in oceanography is this inability to determine the level of no motion. And mathematically, there isn't any. So anyway, to come back to what we were supposed to be doing, there was this supposed breakthrough in detecting U.S. submarines. Walter and I spent the time I was here mainly talking about whether we could put what he knew about acoustics together with what I knew about inverse methods as applied to a completely different problem later on as a justification for the fact that we were here on the military's money. We convinced the Navy, basically, that what they thought the Russians were doing was in violation of some of the fundamental laws of physics, and that this was not a serious threat. So we had a good time that summer, not talking about submarine detection, but talking about acoustics. And the part of the context of this was that, again, look at any textbook, even 10 years ago, this is what the ocean circulation was meant to look like. I think any of the oceanographers from 1900 onward would have said, yeah, that's pretty good. They're gyres, and they're western boundary currents, and a very strong southern Southern Ocean circulation. Walter and I had both been involved in what became known as the mid-ocean dynamics experiment when we came to realize that the ocean didn't look very much like that. It looked more like, which maybe this animation will work. Will it work? Upper.
It's going.
Is it going?
Hit the play.
Hit the play. I don't, oh, I see, okay. Nope. Wrong play button. Help. How do you get it to go? Oh, okay.
You should just be able to click
Fair
on it.
enough. There you go. Is it going? Yeah, okay. This is one of the ECHO high-resolution models, arbitrarily focused in on the Southern Ocean, part of the Southern Ocean. What you would say is, look, it's filled with all these structures. You can see, but you can, for example, see the internal tide passing through southwest. It's full of small-scale eddies. And the question at that point was, of course, we couldn't do that then, with models were nowhere near that good, but we knew the ocean by then was filled with eddies. How do you observe an ocean like that with ships or moorings that cost hundreds of thousands of dollars a piece? And so we kind of thought, well, we can average through a lot of that. Did that thing move at all? Okay, it's visible here. I'm not sure it's visible there. Let me see if I can now stop it and go on. Okay, and we worked out a scheme that Dick Garwin, who at that point I think was the director of Jason, he came into our office one day. We were sharing an office and said, what have you guys been doing? I think expecting to hear about submarine detection. So we explained that we had been putting together acoustics with some rather elementary mathematics. And he was the one who said, oh, you've reinvented tomography. Because I think neither Walter nor I actually made that that connection. And there was, well, the two Jason reports came out of that summer. One of them, the more elaborate one, with Dick Garwin's name on it, and then the one that Walter and I wrote for deep sea research. It was from day one all unclassified, which of course proved important. Tomography conventionally is done on people. And with X-rays, and what you see is this. Is there a pointer? No pointer. No, I'll point. Patient goes into a machine. X-rays are passed from the source to the receiver, and the machine rotates around the patient, and you get integrals along all those straight lines, and medical people and physicists had worked out the mathematics of what you call inverting it. This is a so-called radon transform. There's an inverse, which I won't bother to show you. And of course, it was interesting to know that we had a similar mathematical problem, although apart from the fact that the technology, of course, was utterly different, thinking about a few sources and receivers around edges, we had many fewer things, and then data points. And of course, we had this very interesting fact that the rays were not straight lines, and that was simultaneously a huge advantage because we could see the whole water column top to bottom, but also at the same time an enormous complication that people still work on trying to cope with this. And so this was the origin of it. And then in 1981, Walter and I went off to Cambridge for a sabbatical. We shared an office for 6 months, and we were asked to undertake an exercise in prediction. What would measurements be like in the 1990s? And but here's Walter on prediction. This is a direct quote down there in red. That's well, you can read that for yourself. So, but he did try. We did try to figure out what people would be doing in the 1990s. This is 1981, roughly. And we wrote this paper that appeared in the film Trans, which had some influence, I think. And this is the souvenir that Walter gave me of that time we had together in Cambridge. And it says down at the bottom, "Here's to our tomography fishing on the banks of the Cam." And but we did a certain amount of pub crawling, and I put that in because one of Walter's sayings is you should have fun doing what you were doing. Hangs in my house at home, that picture. What we had in mind was that you could put out a large-scale tomographic array, and you would then combine it with models and anything else you had, shipboard measurements, something of that scale. I mean, that wasn't really a design, but it was meant to be the sort of thing that one could contemplate doing. You would have the whole North Atlantic covered by integration. It finally emerged years later, I would say, as ATOC, which I will not go into. As I said there was a traumatic program which I managed to be out of the country for most of the trauma, but it did come about. It took a while. And I drew this diagram for the Phil Trans paper that Walter wouldn't let me publish because it was meant to show that one could combine tomography with satellite measurements, which were then coming, along with shipboard measurements and models, and put them all together and make a three-dimensional picture of what the ocean was doing. This eventually turned into the World Ocean Circulation Experiment and what we call ECHO. The main failing was our prediction that tomography would be a major component of it. So I must admit that I thought probably won't get the satellites because that involved huge agencies, aerospace agencies, but the tomography we could do. And for reasons that a lot of people in this room know a great deal about, the tomography didn't come along fast enough for us. And the problem of using tomographic data is really the same as what I showed you in that one equation, EX plus N equal Y, set of simultaneous linear equations. In the time-dependent system, which of course we recognized from the beginning, that becomes a gigantic system, and you need clever people to solve the set of simultaneous equations. But I would reiterate that that's really all it is. We're solving a set for the linear problem of simultaneous linear equations by clever means that people have worked out. that's where it came from. I think that to the extent that I would make a prediction that the time is coming when this will play a much more central role in measuring the ocean. I think, as it says there, it was 50 years from the time that John Swallow thought up the neutrally buoyant float to the period when we got Argo. And so I'm guessing that our supposition that it would take less than 10 years to take acoustic tomography from an idea to something that would be widespread was really very premature. And so I will stop there because I think we'll have 2 days of interesting talks about what came of this, and we can exercise a bit of what's in the lower right-hand corner. So thank you.
We have time for a question or two.
Maybe Walter wants a rebuttal.
That was a great talk. Thank you very much. It was a great introduction to the talks that'll occur over the next 2 days. So our next speaker is Brian DeShaw, who is a Walter student. We talked a lot about Walter students. Well, here is one of them, both Walter and Peter. And he's come from Norway, and he'll talk to us about tomography.
Where is... Yo necesito un poco ayuda. Escape? Maybe?
This is adjusted for my height, so maybe we can tilt it up for you.
I think we have to wait for Peter. Well,
Peter's the only one that knows how to do that.
and I don't have a PowerPoint, but I could begin. Peter will be back in a second. So, as you know, I've tried to fight the political fight about tomography and its acceptance, and I've debated the past couple of months as I thought about this talk, how political to be, but I realized that my talk, which we'll get up here in a second. Actually, there it is. It's up on the screen there. Where's the mouse?
Yeah, no, click.
Can you do it?
Peter.
Yeah, so I want to talk about this is basic tomography I'm going to talk about, but having this platform here, I can't help but say what's on my mind and make my case, and so I will say it directly. It may be a little abrupt, but as you can understand, my time is short. I think it's an error by the scientific community not to have implemented tomography and thermometry more widely. That's a scientific error, and it's a due process error, I think. I've been working on this subject now for 20 years, and I honestly can't say I can have witness to an actual substantive discussion of tomography in the Ocean Observing System, tomography with respect to Argo. And even yesterday, talking with John Colosi, there's a general belief that because we have Argo now, we have no need for tomography, and that's just wrong. That's incorrect. There's been publications that have shown that's not correct. And so, speaking of the next 100 years, it's going to start with an actual substantive discussion, substantive studies that are bringing together the acoustic data, the altimetry data, the modeling, to quite explicitly show the various information contents of these. And it's been, as people who know me can tell you, quite exasperating to me to spend the time, the effort to go around to various international conferences expecting to have a say, expecting to have a dialogue, and then not getting it. That's great. So I hope so F11. Fabulous.
Sorry.
Merci. So I hope in the coming years, sooner rather than later, we can start to have that substantive discussion and correct this error. So what I'm talking about today, and I wanted to say, what I'm talking about is not fancy, is not spectacular. This is bread and butter tomography, which I thought would actually be maybe more interesting than trying to say too much. And it's tomography and MEDIs in the Canary Basin. It's examining data collected 20 years ago, Cambios, and it was collected by Fabienne Galliard and Thierry Terre from Ifremer. And a bit of background, I first learned about this experiment about 1996. We went to the Cartwright Tide Symposium at the Royal Society, and I took the opportunity to go across the English Channel and visit Ifremer, and I talked to Fabienne, and they were just about to do this experiment. They got their data back, and they were told to stop working on it after a year or two. There were other priorities, and when they said stop working on it, literally was stop, abrupt. Well, they didn't do that. They wrapped the data up, they archived it, they wrote some nice set of reports that are all available now. And 20 years later, having a bit of freedom and wanting to try living in France for a month, last November I went to Ifremer to take a look at this data. And as we'll see, in many ways, what they were up against, they might not have been able to deal with 20 years ago, that we know about the influence of the small scale. And so for me, seeing this data for the first time and coming from Ferrand Strait, which is all about the small scale, I had some insight into a way forward. So I started working on this project, and a final note, there's a paper involved, but we lost, unfortunately, Fabienne early this year. And so the paper suffers for not having her input. The basic outline of the talk here is to go over some of the original motivations of measurements of MEDIs in the Canary Basin. This is between the Canary Islands, Madeira, and Azores. What is the nature of the Mediterranean water there? What's its transport into the Western Atlantic? And by and large, it's by MEDIs around 1,200 meters near the Sound Channel axis. And the critical thing here, the thing that catches the eye of the acousticians, is the Mediterranean water is warm and salty. It's high sound speed, and typical MEDI is, well, first let me tell you what a MEDI is. It's a salt lens of some 100 meters vertical extent and 100 kilometers horizontal extent that is full of Mediterranean water, warm and salty, and neutrally buoyant, and it travels along the Sound Channel axis by and large. I'll show you some pictures. But it has high sound speed, and so to tomographer, it seems like it's a ripe problem for addressing with acoustic tomography. They're also neutrally buoyant, so they're hard to locate and compute integration, so you can find it by chance with hydrography as they're first discovered, or there's some work on detecting them with satellites that I don't know anything about that, so I won't say anything about them. So a consequence of all this, in 1997, Fabienne and Thierry conducted this experiment, and as Fabienne said, this is a test experiment. They were testing the ability of tomography to measure MEDIs, so keep that in mind. The main issue, the main thrust of the effort here, what I'm talking about, is in the red there, the problem you wrestle with, you research, is can the properties of the received signals be modeled and understood? Can these observations contribute to understanding medwater and transport? And how do you devise an inverse or data constraints that you can use for models? And again, to downplay your expectations, it's going to be trouble. But you'll see. But there's a twist at the end. So the main issue here is this Mediterranean water causes a great deal of acoustic scattering. There's internal waves, but the spice is the main thing. And so scattering dominates over the MEDI signature, so it sort of gets lost in the wash, as it were. And my other main interest here was we have models now for global predictions of mode 1 internal tides. And here was the ripe data just sitting there. Are the internal tides in those data? And then can this global models be used to predict the variability there 20 years after the fact? We'll see if I can get to that. Okay, so to get rid of the top thing, that's all right. Here's the Canary Basin. This is Spain to the upper right there. This is the topography. This is the Canaries down there, Madeira in the middle there, and the Azores. These are the tidal ellipses, never mind. And this was the Cambios experiment, which I'll describe in a few more slides. But this is the geography. It's the Canary Basin. Well, these are MEDIs, and one of the things that's also happened since the past 20 years is they are measuring these things with seismic surveys. And so this is a paper by Papenburg, kind of a famous paper, where they were taking the measurements of seismic surveys in the top panel, which measures the sound speed contrasts, which reveals this extraordinarily fine scale. This is this high salty, high temperature water. Combining that high resolution with an XPT section, which gives a low resolution, to give the bottom panel, which is a really extraordinary image of the sound speed variability, temperature in this case, of this region. I think on the far right is the Strait of Gibraltar with the Mediterranean water coming out. Now, those of you who do acoustics can see right away there's going to be trouble, because this is all this small scale sound speed fluctuating index of refraction is going to cause scattering. It's not just MEDIs. This is another set of data. This is Portugal upper right and Morocco down below. And here's a section across. And there's sub-mesoscale things, cyclones, filaments. I call it litter, a great deal of sound speed litter along the sound channel axis. And I think a lot of it is carried by a MEDI, and you'll see data in a second here. It's surrounded by this spice structure. And so I have this pigpen model where pigpen is the MEDI itself. And as the MEDI goes, it leaves behind this litter along the sound channel axis. Here's a paper from several years ago, 2000, I think, summarizing the locations of MEDIs. These are the red dots, and the general motion of MEDIs moving to the southwest. And so something about them, so they're 15 meters per second sound speed. They circulate at about 20 centimeters a second, and they move, the yellow arrows, at about 4 centimeters a second. And so the Canary Basin is basically a wide channel of movement of Mediterranean water. Here's what a MEDI looks like. In the Cambios, they had a couple of CTDs, the first and second one, where they detected a MEDI. So there's a temperature signature right on the sound channel axis, and then a salinity, high salinity, and then an extraordinarily large sound speed variation. So here is Cambios, and I wanted to emphasize this was a test, and I wanted you to get a sense of the motivation behind the array before I get into the details. There was a span of set of moorings across the Canary Basin, and more MEDIs are moving to the southwest, and so it's a bit of a network to try to catch and monitor and count MEDIs as they're moving to the southwest. Unfortunately, the black lines are all acoustic paths that did not pan out. They had a number of equipment failures, and so the magenta line is all that was measurement. It's a 300 kilometer range. Long story short, they had not multiple hydrophones for beamforming, but in effect, single hydrophone. So there's an issue of resolving upward and downward going acoustics. The sources were 400 hertz with 100 hertz bandwidth, sending to phase-coded sequence, but they were rather weak at 180 dB. So at a range of 300 kilometers, the signals are rather weak. But there were reciprocal acoustics, and so it's a measurement of temperature and current. What's shown here, the figure is from ECHO, this numerical model that Carl was just talking about. This is the sound speed variation at 1,000 meters, showing this diffusion of Mediterranean water southward and to the west. So this is the acoustic data. This is what we have to work with. And it was really quite surprising. First of all, most of our work has been in the Pacific, where we get the deep turning rays arriving first and then the axial rays arriving last. Here it's flipped around. So the It's not the finale in this case, it's the overture thing that's starting. You have a number of stable rays, you see them there. And the top panel shows a cross-section at day 289, so you see where that is. But this, there's no obvious, METI signature that sticks out at you. And then you have this troubling stochastic or random variability in the acoustic reception at the overture. And so the whole research here, the effort is, how can you take data like this? Let's look at the forward problem. Can we devise an inverse problem to extract out information about METIs? And so we'll go through that. So this is the basic arrival pattern, and you can track these time series to get the more oceanographically interesting thing. So this is the track data on the top showing the variation of the travel times. If you take the mean out, some travel times, this is the oceanographic signal, you see the approximate temperature scale on the right. So it's the average temperature in the section is varying by plus or minus 0.4 degrees. And then we have reciprocal transmissions, and so there's currents, which I won't talk much about. Okay. Well, they did a CTD survey over the whole area, and this is a TS diagram showing the isopycnals, and this middle part here is the variation of the Mediterranean water along isopycnals. So there's obviously a METI or two there, and this is this pigpen model. This is this litter that's scattered along the sound channel axis. In the TS diagram as well as in sound speed there. It really is, the Mediterranean water really is focused almost right on the sound channel axis. You also notice the sound speed profile is rather flat, which is causing this reversal of the arrival pattern. Oh, so let me go back here. Mooring T3, you see it there, it failed for acoustics, but there were thermistors and salinity and current measured on T3, and so those all worked. And this is data from that mooring. So here's mooring T3, and you'll see a signal of a METI that's moving to the southwest, and so that when it presumably crossed the acoustic path at some point. The point being, we seem to have evidence that there was a METI. So here's that time series, 275 days. Temperature down below showing it went from ambient temperature of 9 degrees up to 12.5. Big salinity spike of 1 part per 1,000. And you see the current, a little like a hurricane. You have high current, then low in the middle, and up again, and a change in direction. So this is the expected signal that subsequently, perhaps 25 days later, if it's moving at 4 centimeters a second, would have crossed the acoustic path. So why don't we see that in the data? Well, long story short, here are three. So doing the acoustic forward problem, what you want to do is you take the climatological ocean, and you want to add various reasonable things that might be there. And here are three reasonable things. It's a simple METI, just a simple Gaussian. And then we have internal waves. This is the Colosi-Brown internal wave model. They're in the audience today. Thank you, internal wave people. And then this is my quick and dirty estimate for a Mediterranean spice. This is the pigpen model, as it were, showing a clutter or litter of fluctuating sound speed along the sound channel axis. And you'll see here that the internal wave variability is rather weak. It's 0.4 meters per second, whereas the sound speed from spice is a lot bigger. So you can see what that does to these time fronts. This is the arrival pattern as a function of depth. So the top panels, you saw that before. This is the basic arrival pattern. And if you just use climatology, a smooth ocean, you get that arrival pattern, and the depth of the receiver is the horizontal line. And so you get quite a good lineup between the peaks above and the crossings of the receiver depth. You'll notice in the middle, the 4, 5, and the 8, those are doublet arrivals. Those are rays arriving up and down that we can't separate. But you also see on the far right, number 9, there's another reception that was perplexed the ephemeral people for a number of years. How do you get that reception? What's that? Well, if you add internal waves to the climatology, you get the middle panel there, so you get this starts to look like what we observe in the data. But if you add the spice, you get not only this stochastic overture, but you also pick up the zero crossing here. So these have been called shadow zone arrivals or non-geometric arrivals, but those are misnomers. They're not there because the smooth ocean is not a good representation of the real ocean. If you include the small scale that's actually there, they're geometric rays. These are geometric rays. So kind of putting this together, here's what those types of signals would look like. If you had a simple METI as it crossed the acoustic path, it would look like the bottom part. And so you get slight changes in the deturning ray travel times, 10 to 30 milliseconds. But you also get not changes in travel time, but the formation of new rays. And if you have scattering, you get the middle one, which looks like you observed, and then if you put them together, you get the top one, which is on the same scale as the observations. So that seems to be what's going on. But it makes it problematic. In essence, this small scale scattering is obscuring, hiding this kind of small signal of the METI. Remember, the acoustics are measuring a range and depth average, right? It's a very powerful average, and the METI is a small perturbation to it, so it makes it a small signal. And then, meanwhile, you have a METI, and the ray paths start acting weird. The climatology is at the top, and if you have just a simple METI, the rays are now refracted out of the METI. The METI is high sound speed, so the rays are out of it, refracted away. And then you add the small scale scattering. It's pretty severe, but not unmanageable. We could go down that road, but that's all right. You should not be too upset by this. So in close-up, here's the temperature signal observed at the T3 mooring. I shifted it by 25 days, which is about the time that METI would have taken to arrive across the acoustic path. And here is the data that goes with that. So the hope, I guess, would have been that the travel time data would look like this, right? You'd have a single buck. If you don't, you have this broad arrival. It's not a month-long event like the METI is. It goes on for 100 days or so. And I think it's just the scattering is obscure. Now remember, I forgot to say, so this is the temperature. Here's the METI, but you also have this small scale stuff that is around it. It goes with the METI. It's the big band stuff. So this is causing all this scattering. And I think it's really just dominating the whole situation. How much time do I have? 10 minutes? 10 minutes. So I've left out part of the story, which is this acoustic path was on purpose deployed across the Azores front. And I understand the instinct of you want a rich, complicated data, so let's put it where lots of things are going on, but sometimes you can shoot yourself in the foot. And the Azores current may, oh, what happened? A restart required.
You only have 5 minutes now.
Yeah, the Azores current, so you put it in a complicated place, but you shoot yourself in the foot because if too much is going on, then you end up with no answer, right? It could be this, it could be that, and you haven't really. So here's this Azores current. This is a CTD, set of CTDs along the acoustic path, and you see the two clusters, one south, one north of the Azores front. Yeah, so here is, interestingly, I rounded across this paper, I won't pronounce the names there, that shows the latitude of the Azores front at the longitude of 22 west, which is very near Cambios. And this is showing the dotted line is in this soda pop model the latitude of the Azores front, and you can see it just varies widely by 5 degrees or so, peak to peak. And here, over here is Cambios 1997. So that's the slow time series, the slow variations in temperature are probably a consequence of the movement of the Azores front. So here is a tomography inverse solving for the upper ocean temperature along that Cambios path. So it's temperature on the left. And I've converted that over to latitude. So if the signal was caused by the movement of the latitude of the Azores front, that would be the latitude change. So it's changing by plus or minus 1 degree, which is within the realm of possibility for movement. So there, much of the temperature variation may be caused by current movement in that latitude. Just to point out, there are thermistors on the moorings, and they were just flat, and so the Azores current did not cross the mooring, so we have that constraint. Whatever's happening, it's on the acoustic path. Lastly, as I said, one of the motivations for looking at this was the internal tides, and so I have this model now derived from satellite altimetry, an empirical model for mode 1 internal tides, which have shown a great deal of predictability in most regions of the world. And there's a story here. The triangle that said in my dissertation, about 1990, we detected the internal tide variations in those data. And I distinctly remember we had a group meeting at Walter's house discussing this, and Walter declared internal tides are not phase locked. This caused us a great deal of consternation. And so we went back, Peter and I, looking over the light table, Lynn Talley's light table, remember? More emotion, let's look at all the pieces, and it was indisputable these were internal tides. The thing was that it was a 120-day time series, and here was a really regular, like clockwork variation of tides, internal tides, temperature. Some weeks later, after this, I was in Dean Remick's office waiting for something, and Russ Davis wandered in. We went to seeing some internal tides, and here was the response. If I wanted to measure internal tides, all I needed is a thermistor. I thought about this over the years, which this statement is wrong in so many ways. But 3 things come to mind. First of all, this was the basic understanding of internal tides about 1990, right? Secondly, this indicates to me, in retrospect, I didn't have no idea at the time, but in 1990 at least, Russ had no idea as to the essential nature of the acoustic measurement. If someone were to say to me now, measure internal tides in this line average measurement of temperature over 1,000 kilometers, how the hell can that happen, should be the answer, right? Secondly, this is the same attitude. I'm going to start my talk off about Argo. If I wanted to measure the ocean climate, all I need is 3,000 feet. That's the depth of the discussion of the dialogue that I've had. Anyways, this went on. It went downhill from here. Never mind. So here is the same model in Cambios. So remember the topography, it's a basin, and this is the interference pattern by internal tides traveling in various directions. And you might think, how can you possibly predict internal tides there? And the answer is you sort of can. The black line is internal tide mode amplitude, essentially vertical displacement. In this normalization is meters. The blue line is, if you did a tidal analysis of the black line, you would get the blue line. In this case, this accounts for just 20% of the variance. Most everywhere else, this number in the Atlantic and Pacific, this number has been 40 to 70%. So here we're in a region where it's not so predictable. And the red line is a completely independent prediction from the Jason altimetry, showing about the right amplitude as the blue line. The phase seems to be about right. But as I say, so this is great, I thought. So what was come to conclusions? I'll go from the backwards since we were talking about kernel size. We seem to be just partially predictable, but we're in the middle of the Azores current, and I wonder if this internal coherence isn't being disrupted by this current. Previous tomography measurements have been made well from strong currents. So a couple things. This was a test experiment. I can look over here. So the data processing suffered from weak signal to noise. It was a weak acoustic source, and they didn't have beam farming. And so as a test, it's somewhat failing because I kind of want to do it again with a louder source, with multiple hydrophones, and away from the Azores current. The main conclusion here is that spice scattering is important. And we got one, it was a bottom reflected shadow zone arrival. But shadow zone arrival is a misnomer. These are just ordinary rays, but they are induced by acoustic scattering. So this middle one here, whether it's a MEDI or not, you are observing integrated thermal variations in Mediterranean water. But whether the data I've shown can be used to quantify that, it's kind of doubtful, it seems to me. I don't know how to go from the data we've seen here to, it's this many sphere drips of Mediterranean water moving south. And I'll end here with a couple of things. One is I just recently learned that Azores current is a dynamical barrier for MEDIs. You don't seem to find them south of the Azores current. And so this is the twist at the end. This fabulous observing a MEDI current interaction is the current kind of shearing or dragging off small scale variability. This is why we lost the MEDI signature. And lastly, all these data are available, the temperature, slowly, currents, and so forth. So maybe analysis will proceed, maybe it won't. But thanks very much.
Any questions for Brian? Carl?
The altimeter always sees the first which is only so many. Do you distinguish the second and third?
No, the higher modes have zero crossings. So the tomography just measures pretty much mode 1. Just mode 1, because you get
Pretty much.
well, it starts to be an awfully small signal again in a noisy time frame.
Good, Brian. Thank you very much. Another question? Bruce?
Let me start on a little on politics. I had lunch with Neville Smith last May, and he recounted having dinner with Walter and you at Oceanog's 99, the conclusion of which, according to him, was that it was premature for tomography to proceed. I'd be interested to hear Carl and Walter's version.
How much more are you drinking? It doesn't sound like either Walter or me. I certainly don't.
This sounds like a cocktail party conversation. One more question, Art.
We've been encountering this double-ducted phenomenon that you get in your sound speed profiles from some recent work in the Arctic at the moment. We've encountered this double-ducting sound speed profiles in some recent experiments in the Arctic. Peter's been involved with that as well. I've been in a separate experiment, the same double-duct. We've gotten some useful interpretations. I know it's been heresy to you using phrase, but using modes in terms of the traffic that you get to each of those ducts. You're using a floater during source. Just guessing at the width of those, it's only going to support a finite number of modes that are truly trapped.
Right.
You might find some useful interpretations of those that are just trapped.
Okay.
Okay, Brian, thanks very much. Well, so the next talk by Peter Worcester and Bruce Cornell. Peter's going to give the talk, and he's going to talk about ocean estimation using acoustic and non-acoustic data, which I assume will help us understand the spaghetti diagram that Carl put up. Right?
Well, it'll either help you understand it or further confuse you. I'm not sure which. So Carl talked about the beginnings of tomography and the long-held idea, the hope that tomography could be combined with numerical models and other data to give one accurate maps of the ocean mesoscale or the larger scale ocean variability. And we've tried for a number of years to do that, and what I'm going to talk about is an experiment in the Philippine Sea in 2010, 2011, in which all of the pieces finally came together to let us actually do a meaningful data assimilation on a regional scale. But before I get to that, I have to go back and say a little bit about Walter. When I first came to Scripps, Walter was on my qualifying exam, and we'd gone through the exam, and we were walking up the hill from the library toward IGPP, and Walter said to me, more or less something to the effect, how would you like to try measuring ocean currents on 25-kilometer scales using acoustics? And I said, yeah, that sounds pretty interesting. Here I am 45 years later. Well, as part of that, Carl talked about precursors, antecedents to the full development of tomography. And one of those were the 25-kilometer reciprocal transmission experiments I did. We didn't yet understand how to do the inversions, but we were able to combine the data. And Walter and I wrote a paper for ONR's 30th anniversary in 1976 called Monitoring the Ocean Acoustically. And probably the most interesting part of that was they included photographs of us from that era. The one on top still looks pretty much the same. I'm afraid I can't say quite the same for the one on the bottom. So with that, let's go to the Philippine Sea. And what we had was an array that we put out on a scale of 330 kilometers. So this is a 330 kilometer radius. This is Taiwan over here, Philippines here. There were 6 source receiver instruments, transceivers, and 1 receiver. And all of the sources transmitted to all of the other sources and to the vertical receiving array. So we have a large number of crossing paths in a relatively small area. And we'd done experiments like this before, going back to the 1990s in the Atlantic, but we weren't able to do quite the same thing for several reasons. One was the primitive equation ocean models really weren't up to letting us do acoustics in them at the time. They didn't have enough vertical resolution, so that the assimilation that could be done was done in relatively simplified, what are called quasi-geostrophic models. And you don't really need to know what that are, but they're really quite simplified compared to a full eddy resolving general circulation model. We also didn't have satellite altimetry at the time. We didn't have Argo. So even if we'd done something, we didn't really have much to compare it to. Here we kind of had everything. We have satellites, Argo, the acoustics, and the MIT GCM, which gives us a high-resolution regional ocean model. And so really what this talk is about is combining the integral tomographic data, which, as Brian was describing, gives you averages of temperature and current along all of these acoustic paths, with a high-resolution model, using it to constrain the model. Now, this particular region is interesting because it has the second strongest eddy field in the entire North Pacific. Very strong eddy field. It's hard to see, but here's Taiwan. What's shown here is measurements of sea surface height from satellites, and it's showing the variance in the eddy band. So where there's a lot of variance, it means there's a very strong eddy field. The only place that's stronger than where we were working is in the Kuroshio extension up here. Most of our previous work had been over in this eddy desert, which made it very simple. And there's also complicated other things going on that I really won't go into, other currents. This is where the Kuroshio and the Mindanao currents form. So it's an oceanographically highly dynamic and interesting area. It also has very strong internal tides. Now, there are a number of objectives to the experiment. The one I'm going to focus on is the assimilation, and really to see if it's possible to even do that in this highly dynamic, strongly nonlinear region. And we're going to do this in 3 steps. First, we're going to make and test an estimate of the ocean state there using all the other non-acoustic data that's available. So satellite altimetry of sea surface height, Argo data, sea surface temperature data. So we'll first do that, then we'll compute travel times in that model and see how they compared to what we measured. And then finally, we'll go back and recompute the ocean state estimates, including the acoustic data with all of the other data. This is just the details of the MIGCM, probably only of interest to experts, but it's a 1/6 of the degree resolution. Key thing is it has 50 levels in the vertical, so you can really produce sound speed profiles that you can trace rays through. And it's embedded within a Navy model called HICOM ENCODA, which is a worldwide high-resolution model. So this is what we have here is a regional model that just covers the regional area embedded in this much larger model. And the technique that's used is called 4D VAR, and it's okay, you don't really need to understand that, but it's a way of using what's called the adjoint, which basically lets you integrate backwards to figure out what you need to do to the model initial conditions and boundary conditions and forcing in order to make the model fit the data that you have in a consistent way. And when you're all done, the estimate is a free forward run of the model. You just start the model from the initial conditions that you've deduced, and you let it run forward so it's dynamically consistent. So it lets you do dynamically consistent analyses of what the ocean was doing. This is just to show you the data types that are available. There's a lot of data available now that wasn't available in the 90s. This just shows the ground tracks of the various satellites measuring sea surface height. 2010, 2011, there were 3 satellites with quite a dense set of ground tracks. The black dots down here are where Argo temperature and salinity profiles were obtained. And one thing to notice here is, great a tool as Argo is, it's still regions where it's pretty sparse. And that will come back later. This shows the scale of our array here. It's really a regional array. And the color here is the sea surface temperature derived from satellites. This is just the mean over the year, but you have data like that every day. So all of these observations were used to constrain the model. Now, this, as I said, this is a strongly nonlinear region, and the adjoint's a linear method. So it wasn't entirely obvious that this would even work here. And in the model, you set the viscosity and the diffusivity, basically how much like molasses the model is, if you will. And the values here are the ones used in the forward run. And what are plotted, this is longitude and latitude. You can see a little green box in each of these. And what's shown here is for each grid point, in this case, 1 day before the time we're interested in, what is the sensitivity in this box a day later to a 1 meter change in sea surface height at this grid point and that grid point. This is 8 days earlier, 15 days earlier, 23 days earlier. And the basic message here is it gets awfully messy because it's such a strong eddy field. This is what the forward model does, but this is going to make it very, very difficult to do a linear deduction of how the model changes. And so what was done was in the adjoint, much higher viscosities and diffusivities were used to make the model basically calm down the model. It basically changes that extremely complex picture I just showed you 22 days before we're interested in making the estimate, did this much simpler pattern, saying how much, again, a 1 meter change here would result in that green box in this case, 22 days later. And so what happens then is in the adjoint, these higher viscosities and diffusivities are used. And it turned out, although it was not possible to know this a priori, that the large scale of the eddies really allowed this increased viscosity to quell the nonlinearity so that you could actually make the estimates. It would retain the larger scale gradients needed in order to do the assimilation. And it proved possible to do these assimilations over 2-month-long periods. So even though you had this very strong eddy field, one could combine data from 2 months to estimate the state of the ocean. Now, this is an extremely complicated figure that I'm only going to show you a few parts of. What's on the vertical axis is the difference between, in sea surface height, between the model and a gridded set of satellite sea surface height data. And this is a whole year, and each of these vertical lines marks off 2-month periods during which the assimilation was done. So for example, if you look here in May and June, in this 2-month block, all of the sea surface height data, the Argo data, sea surface temperature data were fit to the model using this 4D VAR technique. And what you see happening here now, I'm just going to pick out a couple of the curves. Let's start with this gold curve. And that's the HICOM global model that I mentioned, in which this regional model is embedded. It's not dynamically consistent. It's adjusted every day to fit the data, so that, in fact, you can see here about a 7-centimeter RMS fit, more or less throughout the time period, because that's essentially what it's adjusted to do. And it's not smooth because it's just adjusted from day to day. Well, if you took the MIT GCM and you just initialized it with a HICOM state and let it run, you get this black line. So that's what happens if you just start from the HICOM initial state and let the model run. You can see it starts to differ pretty dramatically from what HICOM was showing. But after you've done the assimilation, you get the red curve. And in this case, it more or less reproduces the precision of the HICOM model that's being adjusted every day, but it's smooth because it's dynamically consistent. It's not being adjusted every day. And as you look through the different 2-month periods, you can see that in general, the model fit is comparable to, or here later in the year, better than the HICOM model. So even though HICOM is using essentially all the same data, in this latter part of the year, this high resolution model, this dynamically consistent, is doing better. So with that, we have an ocean model, and you can kind of summarize the results. This non-acoustic state estimate fits the sea surface height best, but it also fits the Argo TNS, all of the profiles that were there. Turns out that the most important controls are the initial state, the beginning temperature and salinity profile over the region of the model. As I indicated, it's smoother than HICOM, but it doesn't necessarily fit as well at any one time. That depends on the uncertainties you assign to the data and the model. And if you test a future run of the model, in other words, you get to the end of the 2-month period and you forecast forward with a month, which you can do because it's dynamically consistent, you get improvement compared to what would happen if you just ran the HICOM model, if you just started this model from HICOM. So it actually gives you better forecasts for about a month. Now, let's go to acoustic data. This is what the acoustic data looks like. Brian talked a bit about this. This is depth. This is travel time. This is over a range of about 450 kilometers. And on our vertical receiving array, we had a full water column array. And so what you're looking at here is if you set out a single 10 millisecond pulse, it would have the width of one of these lines. But because of dispersion in the ocean, you get this accordion pattern. And if you put a receiver at a kilometer, you see multiple arrivals coming in from a single transmission. It's what Brian was talking about in his talk. And this is for a source more or less on the sound channel axis, around 1,000 meters and around 275 hertz center frequency. So we can measure all these travel times, and this is what you get. This is again the full year. This is travel time. It's a different source-receiver pair. And what's happened is we do a transmission, say, on day 150, and we plot a dot at the time of each peak in the arrival pattern. And the size of the dot depends on the signal-to-noise ratio. The color of the dot depends on the vertical arrival angle. There's a scale over here. We had small vertical arrays at each receiver, so we could measure that. So you get this whole sequence of arrivals. And the variability here of sort of plus or minus 200 or 300 milliseconds is due to the strong mesoscale eddy field. This is kind of an ideal environment compared to what Brian was trying to work with in the Eastern Atlantic. Now, so those are our acoustic measurements. How does that compare with predictions made using the model FIT that we just did using all the non-acoustic data? The solid lines here, let's go down to this one. The solid lines are a filtered version of the plot I just showed you. The internal tides, the high frequency variability has been removed. The crosses are the predictions in the model. With one caveat, there's been 50 milliseconds added to all of the model predicted travel times to make these line up. And there's a couple things you see. This, I think, was the first experiment in which we were able to predict from non-acoustic data the mesoscale variability that we measured. We'd never done that before. But it's not perfect, but it shows, I think, the extent to which the whole system is hanging together. The simulation process, the model, the acoustic data, everything's fitting. But there are still differences. There's this 50 millisecond offset. The fact that we had to add 50 milliseconds to the model means the model was too warm somewhere. The travel times were higher. So the predicted arrivals were coming in too early. And there's also detailed differences here. The extent of the difference varies from time to time, but it's of order of kind of 50, 60 milliseconds, depending on the time of year. And our precision in travel time is down at something like 10 milliseconds. So these small differences are, in fact, significant and can be used to constrain the model. So we did that. And what you can look at to assess how this is working is the cost. It's basically a measure of the misfit between the model and the data. And what we did was we took the final constrained version of the model using all the other data, the one used to predict the travel times, and we then added in the travel time data as another constraint. And when you do this process, you iterate the model. You go through multiple steps because it's nonlinear. And so you can look at how well, basically, the model fits all the various data types. So on this plot, the red bars are the first iteration, the 7th iteration, the 13th iteration. This is sea surface height, and it's basically showing you that because we'd already fit the sea surface height, it still fit. And it didn't really change as you iterated. Over here, Argo, temperature, and salinity, we'd already fit them, and so they still fit. The acoustics, however, had a substantial misfit when we first did it. But as we iterated it, that misfit was reduced down to the expected level, the expected travel time precision. And the interesting thing was it proved possible to do that without disturbing the fit to any of the other data. The ocean essentially has enough unresolved variability, even with all the other data we collect, that the acoustics was still making measurements of ocean variability that had, if you will, slipped through all of the other measurements. Now, what did that look like? The This shows a 2-month period. This is 60 days. And this is the travel times, the data minus the model predictions. And when we started, it's all, and this is just a ray counter. So there was 300 some ray paths, 60 days of data. And the fact this is all red and yellow means that all of the model travel times were too small. The sound was traveling too fast. After the fit, these shaded colors indicate that we're fitting the data, and everything is just fine. This is for 1 2-month period in May and June, and this started again from the initialized solution without the acoustics. So it really all held together, and you can see that perhaps more simply in a simpler plot if you just look at the travel times. So this is the mean travel time difference over the year. This is from the optimization without the acoustic data, and this is the optimization with the acoustic data. This is 20 milliseconds per tick. So it's, on the mean, it fits within a few milliseconds. This is the standard deviation, and you can see before it's kind of order 30, 40 milliseconds. Afterwards, it's kind of 10 to 15 milliseconds over the whole year. Now, what does that mean in terms of the change to the ocean? So this now is a plot as a function of depth of the mean difference between temperatures measured at the DVLA, which were not used in the assimilation, and the model temperatures. And from the fit to the non-acoustic data, you get this black line, which you can see has a negative temperature anomaly of several tenths of a degree between about 500 meters and 1,500 meters. And once you've added in the acoustics, it essentially removes that so that the model fits the DVLA data, which is completely independent. It wasn't used. So even with all these other data types in around the depth of the ocean sound channel, you could have discrepancies of order several tenths of a degree. And I think perhaps one should say the reason that can happen is because while we fit all of the Argo T and S data, it was still relatively sparse in that region. So it's not that the Argo data was wrong, it was just relatively sparse. And by an accident, we didn't happen to have enough floats in that area to accurately predict what was going on. I mentioned doing forecasts. If you start from the optimized model with the acoustics and look at the travel times, forecasting forward a month. So each of these little bars is a month. The forecasts really stay quite good for about a month when you've fit the model to the acoustics as well as all the other data. But if you just use all the other data, your errors are of order 100 milliseconds. You don't do nearly as well. These are just the standard deviations which show the same thing. So the summary is really a true statement. I don't want to belittle how well we're doing in measuring the ocean now. The estimates made using all of the non-acoustic data fit the acoustic data remarkably well. There are still significant differences, and when we incorporated the state estimates, we found this temperature bias, whatever you want to call it, at 500 to 1,500 meters depths. And it also improved the temperature forecasts, although I didn't show that. So I'd like to just close with a quote from Walter and myself. Observing the oceans without sound waves is like observing the atmosphere without electromagnetic waves. Both are unthinkable. And what I think is likely to happen, the modeling that was done here was part of together with modeling done for the OKMC project, the origins of the Kuroshio and Mindanao Current. And what you saw happening there was this same model was being used to help interpret the data they measured. And I think in the long run, what you're going to see is whatever the data type, it'll end up being combined with the models, and people will end up analyzing those dynamically consistent solutions, if you will. And then the problems, the difficulties associated with the fact that acoustic data is in some ways more difficult to think about or handle than a profile will kind of go away. It'll be like our use of satellite altimetry data. I mean, how many of the people who use sea surface height data have any idea of what went into getting that sea surface height? They just take it as given. And I think the same thing's going to happen in the long run for all the other data types. And with that, I would like to thank Walter for 40 wonderful years. This is Walter and myself in 1988 in the Blue Lagoon in Iceland after we'd put out a tomographic array up in the Greenland Sea. Thank you.
Lots of time if people have questions.
Have you tried the complementary simulation experiment in which you only use the tomographic data and then see whether it will drive down the other cost terms, for example, for Argo as well, without actually using to see whether there's sort of an implied benefit of the tomographic data?
That would be an interesting experiment to do, but we haven't really done it. And, you know, when I say we, Bruce and Ganesh Gopalakrishnan are really the ones who did all of this. I'm more or less the front man here. But no, we haven't done that. It would be an interesting experiment to do. Rob?
Are these edge rate approaches essentially endless in the sense that you're always getting a better fit as you add a new data type? Is there some way, you know, suppose the measurement system of the future just blows away everything we have now, and you have 10 times as much data, and you fit the new measurements along with all of the old ones. Will you ever get a situation where the system tells you we don't need any more measurements, it's good enough? Or do you always get a better fit because you're minimizing something?
Well, I'll try it. I'll take a stab at an answer, and Bruce can correct me if I'm wrong. But I think, you know, you're doing the fits within the uncertainty. So at some point, it's just going to say you're fitting as well as you can with the uncertainty, and you're really not gaining anymore. And in fact, one of the questions here was when we added the acoustics, given all these other data, would it really make any difference? And we didn't really know the answer a priori.
Well, the ocean changed, but your ocean model gave a different answer, but the discrepancy with all other data types really got changed.
Right, well, that tells you you're still under-resolved with all the other data types.
Yeah, it seems, how do you know when you've done enough?
You want to take a stab at that, Bruce?
100 years.
I'd like to have Carl explain this study. We just talked about at the beginning. You have an infinite number of solutions. You don't have that many data. And you knock them out every time you take data. You can knock out one or more solutions, but there's always a bunch left over. Whether you care about that uncertainty or not is the thing. Uncertainty is very expensive to calculate. Patrick is sitting behind you. They've actually worked on calculating it very rigorous way, which is very expensive. You can also do it other ways, and so you can actually get an error map. You should never put in a map without an error map. But we didn't do that because it's expensive. But you can see where you know and where you don't know.
I'm going to stop because Walter wants to say something.
Okay.
Stop. Okay, if it's a short one, because I want to leave a little bit time for.
What is 40 bar doing for the boundary conditions and the forcing to make everything fit?
It's adjusting them some, and over 2 months, it's hard to distinguish. Like the boundaries are far enough away, they don't have that much of an effect on the observations that we use, and the initial conditions tend to dominate. But
It also adjusts the wind forcing too, right? Or,
yes,
yeah.
and in the version that Patrick and Carl and Detlef Schammer and other people did when they developed the ecosystem, they tried to do it over the most period, 20 years or more, and then initial conditions aren't important at all, and you're really trying to diagnose an ocean that's in equilibrium, which is forcing, and where the forcing and the observations all make sense. And we're just kind of a radical, crazy, short-term variant of the redheaded stepchild, the echo.
I'm going to take the liberty of allowing you to continue this conversation during the coffee break, but before we break, Walter would like to say a few words. Do you have a photo mic? Pardon? Is there a clip-on mic? No. I don't think so.
Well,
Move up here, so you can move up to the...
I want to say thank you for coming here. It's given us tremendous pleasure. I'm impressed with how lucky I was to choose the time to have my career. Margaret's remarks, very gracious remarks, reminded me how much good association and friendship I had with the various directors. Harold Sverrup was my teacher and became my good friend for the rest of my life. Roger Abel is one of my heroes throughout his entire career. And then there have been many others, including Charlie Kennel, Ed Freeman, and now Margaret, with whom I have a very warm and positive relation, and I thank them for having let me work with them. Now, another very lucky coincidence is that my career overlapped with the formation of ONR. And I'm so pleased Frank Herr is here today. We started just about the same time. We're not going to end the same time, but the fact that I started with ONR and went through the development of ONR has led to a lifelong relation with the Navy, which has been just absolutely a centerpiece of my existence. And thank you, ONR, and thank you to the Navy for having made this possible. And otherwise, I must emphasize my thanks to Bob Spindel for chairing this meeting. He's a lifelong friend. To Carl Wunsch, with whom I've worked probably more than anybody else. Peter Wooster, as he said, 40 wonderful years of collaboration. Bruce Cornell, who also organized this meeting. I think I first met you on the Big Island at your parents' house. Is that correct? Many, many years ago. And so I have had a great deal of luck of choosing my friends, my directors, my associations with the Navy, and my partners with whom I've worked throughout my life. Thank you for coming. Thank you. That's all. That's all.
Okay. I think we can take a break and we'll back here.